So here's the thing about the Hubble Space Telescope. For most of our lives, it was the undisputed champion of the cosmos, the greatest observatory ever built. It floated up there, high above the Earth's atmosphere, and it spent 30 years taking the most incredible baby pictures of the universe we had ever seen. It showed us things we never dreamed of, galaxies colliding, stars being born. It completely rewrote our understanding of space. But it had a wall, a fundamental limit it could never get past. For all its power, Hubble could not see the beginning of time. Now that sounds weird, right? It's a telescope. It sees light. And the further away it looks, the further back in time it sees. So why couldn't it just keep looking further and further until it saw the very first stars and galaxies switch on? The problem wasn't the telescope. The problem was the universe itself. The universe is expanding. It's been expanding for 13.8 billion years, and that expansion does something very strange to light. Imagine you draw a wave on a rubber band, and then you stretch that rubber band. The wave gets longer, right? The peaks get further apart. The same thing happens to light traveling across the expanding universe. The further it has to travel, the more it gets stretched out. Light from the very, very beginning of the universe has been traveling for over 13 billion years. It's been stretched so much that it's not even visible light anymore. It's been stretched all the way down into the infrared part of the spectrum, which is basically heat. So the oldest light in the universe isn't a twinkle, it's a faint cosmic glow. And this was Hubble's wall. Hubble was designed to see the universe primarily in visible and ultraviolet light, the same kind of light our eyes see. It was like trying to see in total darkness with a pair of sunglasses on. It just wasn't built for the job. It could catch a tiny bit of the near-infrared stuff, but the really ancient, really stretched out light from the dawn of time was completely invisible to it. Hitting this limit wasn't a failure, though. It was the most important discovery Hubble ever made, because it told us exactly what we had to do next if we ever wanted to see how it all began. So this stretching of light has a name. It's called cosmological redshift, and it's the biggest headache for anyone trying to look back to the beginning of time, because it makes everything incredibly counterintuitive. You've probably experienced something similar with sound. Think of an ambulance siren. As it comes toward you, the pitch is high. As it moves away, the pitch drops. That's the Doppler effect. But what's happening to the universe is weirder. The galaxies aren't just flying away from us through space. The space between us and them is literally getting bigger. The rubber band is stretching. Visible light is a spectrum like a rainbow. On one end you have blue and violet light, with short, tightly packed waves. On the other end you have red light, with long, stretched-out waves. When the universe expands, it stretches those light waves, shifting them toward the red end of the spectrum, hence redshift. But what happens when you keep stretching? The light doesn't just stop at red. It gets stretched right past it, into the infrared, then into microwaves, then into radio waves. The longer it travels, the more it gets stretched, and this is the cosmic punchline. The very first stars in the universe were probably not faint and red. They were monsters, massive, brilliant, blue-hot giants, 100 times bigger than our sun, burning themselves out in a cosmic blaze of glory. We should be seeing this incredible violent fireworks show. But we don't, because that brilliant blue light has been travelling for over 13 billion years. It's been stretched and stretched and stretched until it's not blue anymore. It's not even red. It's deep, deep infrared. It's basically just a faint ancient heat signature. It's like taking the highest note on a piano and stretching the sound wave until it's the lowest, rumbling bass note you can imagine. So low you can't even hear it anymore, you just feel it. That's what we're looking for, not a twinkle, but a vibration. So, to see the birth of the universe, we couldn't just build a better Hubble. We had to build a completely different kind of machine. We needed a telescope that could see in the dark, a telescope that could see heat. We needed a time machine, and we needed to build it to see a kind of light that is totally invisible to our own eyes. So, okay, we need a telescope that can see heat. Sounds simple enough, right? We have thermal cameras, we can see heat signatures all the time, but there's a huge, brutal catch. The kind of heat we're looking for, the faint infrared glow from the first stars, is the oldest, weakest, most stretched out light in the entire universe. And the universe is full of other things that are hot. Very, very hot. Trying to see the first stars with an infrared telescope is like trying to spot a single firefly from 100 miles away while you're standing right next to a bonfire. The firefly is the ancient star. The bonfire is, well, everything else. The sun is a bonfire. The earth is a bonfire. Even the moon, just by reflecting sunlight, is a bonfire. Any of that heat, any of that nearby infrared light, would completely blind the telescope. It would be like trying to hear a whisper in the middle of a Metallica concert. Total sensory overload. But the biggest problem, the real headache, isn't even out there in space. It's the telescope itself. The electronics, the computers, the communications gear, all of that stuff generates its own heat. So it's not just that you're standing next to a bonfire, it's that you yourself are also on fire. The machine we build to see the heat of the Big Bang has to be invisible to itself. This means the entire observatory has to be kept cold. Not just a little chilly, we're talking insanely, absurdly, fundamentally cold. The target temperature for the telescope's mirrors and instruments was about -223 degrees Celsius. That's 50 degrees above absolute zero, the point where atoms themselves practically stop moving. For a little perspective, the coldest temperature ever recorded in Antarctica was about -89 degrees. The surface of Pluto is around -229. So, to see the birth of the universe, we had to build a machine and keep it colder than the surface of Pluto. We had to shield it from the sun, the earth, the moon, and even its own guts, all so it could catch the faintest, most ancient heat imaginable. This wasn't just a matter of building a bigger telescope, it was an engineering challenge unlike anything we had ever attempted. This is the point where the story pivots from a physics problem to a political one. The year is 1996. Hubble has been a wild success, and the scientific community is buzzing with what to do next. The plan was formally kicked off for what was then called the Next Generation Space Telescope, or NGST. And it was born into a very specific moment in NASA's history, the era of faster, better, cheaper. This was the mantra of the time. The idea was to move away from the gigantic, decade-spanning, budget-breaking projects of the past and toward a new fleet of smaller, more efficient missions. It was a nice idea, a sensible idea. And for this new telescope, it was a completely impossible idea. The initial proposal was for a telescope with a mirror 8 meters across. For comparison, Hubble's mirror was 2.4 meters, so a huge leap in size and power. But the engineers immediately hit a wall, a very simple, very solid wall. The problem was the rocket. The biggest rocket fairings we had, the nose cones that protect the payload on the way up, were only about 5 meters wide. It's a basic geometry problem. You can't fit an 8-meter wide dinner plate into a 5-meter wide pizza box. It just doesn't go. It was like trying to get a king-size mattress up a spiral staircase. The math just isn't on your side. This meant the mirror couldn't be a single solid piece of glass like Hubble's. It had to be built in pieces, like a honeycomb, and it had to fold up. The entire telescope would have to be packed down like a piece of high-tech origami, stuffed into a rocket, and then unfold itself perfectly, millions of kilometers from Earth, with no one around to fix it if it got stuck. And remember that other problem? The cold? This whole complex, unfolding machine still had to be kept colder than the surface of Pluto, which meant it needed a sunshield, a massive one. The early designs called for a multi-layered shield the size of a tennis court, which, you guessed it, also had to be folded up to fit in the rocket. So let's just recap. We needed a segmented 8-meter mirror that could fold. We needed a tennis court-sized sunshield that could fold. We needed to keep the whole thing at -223 degrees Celsius, and we needed to do it all faster, better, and cheaper. The engineers looked at the list of requirements, and they looked at the laws of physics, and they knew one of those things had to give, and it wasn't going to be physics. The cheaper part of the plan was dead on arrival. This wasn't going to be a sequel. It was going to be a complete reinvention of what a space telescope could even be. So, the whole faster, better, cheaper idea was officially in the trash can. The engineers and scientists were now playing a different game, a much more serious one. The game was called, what is the absolute minimum we need to see the beginning of time, and is that even physically possible? Let's talk about how a telescope works. At its heart, a telescope is just a light bucket. The bigger the opening of your bucket, the more light you can collect. If you're looking at something bright and close, like the moon, A small bucket is fine. But if you're trying to catch the faintest, oldest, most stretched out photons in the entire universe, photons that have been travelling for 13.5 billion years, you need a ridiculously big bucket. The team ran the numbers. They calculated how faint that ancient light would be. They argued. They went back and forth. The initial 8-metre dream from the early days was just too much. Too big, too heavy, too complicated. So they scaled it back, shaving off every centimetre they could without sacrificing the entire mission. They finally landed on a number. The absolute minimum size for the primary mirror was 6.5 metres across. That's more than 2 stories high. And this is where they ran, once again, into that same simple, brutal wall of geometry. The biggest rocket fairing in the world was still only 5 metres wide. A 6.5 metre mirror does not fit in a 5 metre tube. It's not a failure of imagination, it's just a fact, like trying to park a bus in a standard-sized garage. You can try all you want, but you're just going to make a mess. So if you can't build a rocket big enough for your mirror, you have to build a mirror that's small enough for your rocket. But if you do that, the bucket is too small, and you can't see the first stars. The mission is a failure before it even launches. It was a paradox, a physical dead end. Unless you break the mirror, not literally smash it, but build it in pieces. The solution was as elegant as it was terrifying. They would construct the mirror from 18 individual hexagonal segments, made of beryllium and coated in a microscopically thin layer of pure gold. Together they would form a single, perfect, 6.5 metre light bucket. And to get it into the rocket, the whole thing would fold up. 2 side panels of the honeycomb, 3 mirrors each, would fold backwards. The entire telescope, a machine the size of a small building, would be contorted like a piece of high-tech origami to fit inside its ride to space. This was the plan. A plan that relied on 100 different mechanisms working perfectly, 1,000,000 miles from home, in the freezing cold. They weren't just folding up a satellite dish. They were folding up the most sensitive and precise mirror ever created, and they would have one chance to unfold it. No second tries, no repair missions. So this was the plan. The only plan. Break the mirror into 18 pieces, fold it up like a piece of cosmic origami, and hope for the best. Now why hexagons? It's the same reason bees build their honeycombs that way. It's the most efficient shape to cover a surface without leaving any gaps. No wasted space. You get the biggest possible mirror packed into the tightest possible area. Nature figured it out a long time ago, we were just catching up. And these weren't just any hexagons. Each one was carved from a block of beryllium, which is this super weird, super light and super strong metal. It's great because it doesn't warp or bend when you get it down to Pluto-level temperatures. Then they coated each one in a layer of pure gold so thin you could practically see through it. Not because it looks cool, though it does, but because gold is basically a perfect mirror for infrared light. It's exactly what you need to see the heat from the beginning of time. The layout was simple enough on paper, a big central section of 12 mirrors, with 2 wings of 3 mirrors each that would fold back for launch. But the reality was insane. After the telescope got to its destination, 1,000,000 miles from Earth, it would have to wake up and perform the most delicate robotic ballet ever attempted. First, the wings would have to swing forward and latch into place. Then, each of the 18 individual mirrors, each one sitting on 7 tiny motors, would have to adjust itself. And we're not talking about adjusting a car's rearview mirror here, we're talking about movements smaller than a virus. Each segment had to be aligned with the others to a precision of about 10 nanometers. To put that in perspective, a single sheet of paper is about 100,000 nanometers thick. If the alignment was off by even a tiny fraction, the whole 6.5 meter mirror would be useless. It would be like looking through a funhouse mirror. The images of the first galaxies would be a blurry, distorted mess. This whole process would take weeks, 126 tiny motors, plus all the latches and hinges, all working in perfect sequence, all commanded from Earth by a team of engineers who could do nothing but watch and pray. There were hundreds of single points of failure, hundreds of ways for this $10 billion time machine to become the world's most expensive piece of space junk. And as if that wasn't terrifying enough, this whole delicate golden flower was just one part of the origami puzzle. Because even if the mirror unfolded perfectly, it would be instantly blinded by the heat of the sun. They still had to solve the other problem. the bonfire problem, they needed a parasol, a giant 5-layered tennis court-sized parasol that also had to unfold itself. Okay, so we've talked about the insane origami plan, folding up the most precise mirror ever built, shipping it 1,000,000 miles away, and then hoping it unfolds itself perfectly. But in all of that, we've actually skipped over one of the most fundamental headaches the engineers had to solve. Before you can figure out how to fold a mirror, you have to figure out what on earth you're going to make it out of. The obvious choice, the one everyone would think of first, was glass. It's what Hubble's mirror is made of. It's what most big telescope mirrors on Earth are made of. It's a known quantity. But for this mission, glass had a fatal flaw. Remember, this telescope has to be kept colder than the surface of Pluto. And when you get glass that cold, it shrinks. A lot. And worse, it doesn't shrink perfectly. It warps and deforms. A mirror that needs to be accurate to the width of a single virus can't be made of something that changes its shape just because it gets a little chilly. The image would be a blurry mess. So glass was out. The engineers went on a hunt for a miracle material. They had a checklist of impossible demands. It had to be incredibly lightweight, because every kilogram you launch into space costs a fortune. It had to be immensely stiff, so a 2-story tall mirror wouldn't sag or bend under its own weight. And the most important thing, it had to be thermally stable. It had to hold its perfect polished shape when cooled down to minus 223 degrees Celsius. And after looking at everything, they found it, a strange exotic metal called beryllium. This is where the story gets properly weird. Beryllium is one of the lightest solid metals that exists. It's lighter than aluminum, but it's 6 times stiffer than steel. It's an absolute freak of nature. And crucially, when you cool it down to cryogenic temperatures, it basically just doesn't care. Its shape is rock solid. It was the perfect material for the job. Except for one tiny, terrifying detail. It's also incredibly toxic. We're not talking about don't lick the spoon toxic. We're talking about if you breathe in a microscopic particle of its dust, it can cause a fatal lung disease toxic. Machining these mirror segments was an absolute nightmare. The technicians had to work in full-body hazmat suits, breathing supplied air just to grind and polish the metal. It was a slow, dangerous, and brutally expensive process. One slip-up, one crack in the brittle metal, and a multi-million-dollar mirror segment could become a piece of toxic scrap. So why on earth would they choose this horrible poisonous stuff? Because they had to. It was the only material in the known universe that ticked all the boxes. The only thing light enough, stiff enough, and stable enough to build a mirror that could survive the journey and see the beginning of time. It was beryllium, or the mission was impossible. So they tamed the toxic metal, and they built their golden honeycomb. The mirror problem was solved. But that just brought them right back to the bonfire problem. Even a perfect beryllium mirror is useless if it's being cooked by the sun. They still needed that parasol. So they picked their poison. Literally. They chose this incredibly toxic, incredibly difficult metal, beryllium, because it was the only thing for the job. But here's the thing. Just having the right material for your mirror is like having the right kind of flour to bake a cake. It's a good start, but it's not the cake. The real work, the part that makes or breaks the whole mission, was in the finish. Each of those 18 hexagonal segments had to be polished to a level of smoothness that is almost impossible to imagine. We're not just talking shiny. We're talking about a surface so perfect that if you scaled one of these mirrors up to the size of the entire United States, the biggest bump on it would be less than 3 inches tall. Any flaw, any microscopic ripple in the surface, would act like a tiny bit of fog scattering those precious ancient photons from the first stars. The mirror couldn't just be good, it had to be perfect. And once they had that perfect shape, they had to make it reflective, and not just any kind of reflective. Remember, we're looking for infrared light, heat. And it turns out the absolute best material in the universe for reflecting infrared light is gold, but you can't just slap a layer of gold paint on it. The coating itself had to be as perfect as the mirror underneath. They used a process called vapor deposition, which is basically like spray painting with individual atoms. They put the mirror segment in a vacuum chamber and released a tiny puff of gold vapor, which then settled onto the surface in a layer just a few hundred atoms thick. How thin is that? About 100 nanometers. A human hair is about 700 times thicker. The amount of gold used for the entire 6.5-meter mirror was less than 50 grams. You could make a wedding ring out of it and still have some left over. So that's what it all comes down to. This entire multi-billion-dollar time machine, this giant piece of origami, is all just a delivery system for a layer of gold so thin it's barely even there. That's the surface that will catch the first light. That's the bucket. And with that, the mirror was finally ready. A perfect golden eye, polished to near atomic perfection, ready to stare into the dawn of time. There was just one last, giant problem. It was still standing next to a bonfire. So how do you solve the bonfire problem? You have this perfect, golden, hypersensitive eye, ready to see the dawn of time, but it's being constantly cooked by the sun, the earth, and even the moon. You can't just put it in the shade because there is no shade in space. You have to bring your own. You need that parasol we talked about, a giant, planet-sized umbrella. This is where the story gets another layer of insane ambition. The solution was called the Sun Shield, and when we say it was big, that doesn't really do it justice. The plan was to build a 5-layered shield the size of a tennis court and fly it 1,000,000 miles from Earth. The job of this shield wasn't just to block sunlight like a pair of sunglasses. Its job was to create one of the most extreme temperature differences in the entire solar system. The goal was to create a temperature drop of nearly 330 degrees Celsius. That's almost 600 degrees Fahrenheit, from the hot side to the cold side. The sun-facing side would get hot enough to boil water. The telescope side, just a few feet away, would be colder than the surface of Pluto. Now you might be thinking, why 5 layers? Why not just one really thick one? It's the same reason a thermos keeps your coffee hot. The real magic isn't the material itself, it's the vacuum between the layers. Each layer of the sun shield blocks some heat, but it also radiates a bunch of it out into space from the sides. The first layer gets baked, but it protects the second layer, which is a little cooler. That one protects the third, which is cooler still. By the time you get to the 5th layer, on the telescope side it's in a permanent deep freeze shadow. And what was this miracle shield made of? A material called Captain. It's basically a high-tech, super thin, super tough plastic wrap coated in a layer of aluminum and silicon. It's strong enough to survive a rocket launch, but thin enough that you could tear it with your hands if you weren't careful. So let's just put this all together. To protect the most expensive mirror ever built, the plan was to deploy a 5-layered, tennis court-sized kite made of delicate plastic wrap. And of course, just like the mirror, this entire massive, fragile structure had to be folded up like an accordion, stuffed into the same tiny rocket, and then unfold itself perfectly in the middle of nowhere. The origami problem just got a whole lot bigger. Okay, so we have this giant 5-layered tennis court-sized kite made of delicate plastic wrap, and we've folded it up like an accordion. Simple enough. But now comes the truly terrifying part, unfolding it. This wasn't like popping open an umbrella. The deployment of the Sun Shield was one of the most complex mechanical sequences ever designed for a space mission. It was a slow, deliberate, multi-day ballet of motors, cables, and pulleys. A high-tech Rube Goldberg machine where every single step had to work perfectly. Let's just run through the inventory. The system involved 140 release mechanisms, 70 different hinge assemblies, 8 deployment motors, something like 400 pulleys, and 90 individual cables that, if you laid them end to end, would stretch for almost 1/4 of a mile. All of this to pull 5 membranes thinner than a human hair into a perfect taut diamond shape. Imagine trying to untangle the world's most complicated fishing net in the dark while wearing oven mitts. Now imagine that if a single knot gets stuck, a $10 billion mission is over. That's what we were dealing with here. This is what engineers call single points of failure, and the Sun Shield was absolutely riddled with them. A motor could burn out. A cable, some of them no thicker than a fishing line, could snag on a pulley. A latch could fail to release. Any one of these tiny individual failures would stop the whole process dead in its tracks. The shield would be half deployed, the telescope would be cooked by the sun, and the whole thing would become the most expensive piece of space junk in history. There was no backup plan, no astronaut repair mission like with Hubble. This was a one-shot deal, 1,000,000 miles from home. The entire fate of the mission, our one chance to see the beginning of time, rested on this insane high-wire act of mechanical origami working perfectly. And this was just the first act. The mirror was still tucked away, waiting for its turn. So, you have a plan that involves a toxic metal mirror, a layer of gold thinner than a human hair, and a 5-layer tennis court-sized kite. A plan that relies on hundreds of pulleys and cables, and motors all working perfectly after being folded up like a piece of high-tech origami and shot 1,000,000 miles into space. What could possibly go wrong? Well, the first thing that went wrong wasn't a snagged cable or a burnt-out motor. It happened right here on Earth in a spreadsheet. All of this mind-bending complexity, all of this one-of-a-kind engineering came with a price tag, and that price tag started to grow, and then it just kept growing. The project was originally pitched in the late 90s with a budget of around $1 billion and a launch date of 2007. It was ambitious, but it seemed manageable. But as the true, brutal scale of the engineering challenges became clear, the timeline slipped and the costs spiraled. By 2011, the estimated cost had ballooned to nearly $9 billion, and the launch date had been pushed back more than a decade. This period became known as the Decade of Delay. And this is where the project had its near-death experience. The US Congress, looking at the ever-growing bill, decided it had had enough. A House of Representatives committee voted to cancel the entire project, to pull the plug. After more than a decade of work, after inventing new materials and solving impossible problems, the whole thing was almost thrown in the trash. It was only saved by a massive effort from scientists and supporters who convinced the government to see it through. But this event changed everything. It established the incredible crushing pressure on every single person working on the telescope. They weren't just fighting the laws of physics anymore, they were fighting a ticking clock and a skeptical government. And they were doing it all with one terrifying fact hanging over their heads. Unlike Hubble, which orbits just a few hundred miles up, the James Webb Space Telescope was going to be sent 1,000,000 miles away, 4 times further than the Moon. There was no way to fix it. No astronaut repair mission. No sending up a new part if something broke. Every single one of those hundreds of single points of failure we talked about had to work. The first time, because there would be no second time. It was perfection, or it was a $10 billion piece of space junk. So you've built the most expensive, most complicated, most sensitive telescope in human history. Where do you park it? The obvious answer, the one that seems to make the most sense, is to just put it in orbit around the Earth, like Hubble. But for this mission, that's a terrible idea. Remember the bonfire problem. The Earth is a giant bonfire of heat. The Moon is another one. If the telescope is orbiting the Earth, it's constantly moving in and out of the planet's heat and shadow. The sun shield would have to constantly reorient itself, and the telescope would be constantly warming up and cooling down. It would be a thermal nightmare. We needed a place where the sun, the Earth, and the Moon were always in the same direction. A place where we could point our giant tennis court-sized parasol at all 3 bonfires at once and just leave it there forever. And it turns out a place like that actually exists. It's called a Lagrange point. It's a weird little pocket of space where the gravity from the sun and the Earth do this funky little dance and basically cancel each other out, letting a small object just hang there. The physics is pretty complicated. I wouldn't worry too much about it. The point is, these are the solar system's premium parking spots. There are 5 of these spots, but we were interested in one in particular. Lagrange Point 2, or L2. It's located about 1.5 million kilometers away from Earth, on the exact opposite side from the Sun. That's 4 times further away than the Moon, and this is the genius of it. From L2, the telescope is always looking at the Sun, the Earth, and the Moon all lined up behind it. It's the perfect setup. The sun shield has one permanent job: block the 3 biggest sources of heat in our neighbourhood. And the telescope itself can live in a constant deep freeze shadow, staring out into the darkness of deep space. But of course it's not that simple. L2 isn't a perfectly stable parking spot. It's more like trying to balance a marble on top of a beach ball. It's a point of equilibrium, but a wobbly one. So the telescope can't just park there and switch off the engine. It has to constantly fire its little thrusters to stay in what's called a halo orbit around L2, making tiny corrections so it doesn't drift away. It's not parked, it's hovering. So that was the destination. Not a simple orbit. but a weird, unstable gravitational eddy a million miles from home. It was the only place in the entire solar system that could give this $10 billion time machine the cold and the dark it needed to see the beginning of time. So after decades of work, $10 billion, and one near-death experience in Congress, the moment finally arrived. On Christmas Day 2021, the James Webb Space Telescope, folded up inside the nose cone of a European Ariane 5 rocket, was sitting on a launch pad in French Guiana. The entire world was watching, no pressure. The rocket's job wasn't just to get this thing into space, it had to fling it on a very specific, very precise trajectory toward that weird gravitational parking spot, L2, 1.5 million kilometers away. It's an incredibly difficult shot to make. The rocket has to provide the exact right amount of thrust, for the exact right amount of time, in the exact right direction. One tiny error, and the telescope would either miss its target completely or have to burn a huge amount of its own precious fuel to correct the course. The launch was flawless. The rocket roared to life, and for 27 minutes the team on the ground could do nothing but watch and hope. The telescope separated from the rocket, its solar panel deployed, and it began its long, lonely journey. A complete success. But then, as the engineers started looking at the telemetry data, they realized something incredible. The launch wasn't just a success. It was perfect. Impossibly, absurdly perfect. See, the telescope has its own small tank of fuel. This fuel is for two things: making small course corrections on the way to L2, and then firing its thrusters for the next decade or so to stay in that wobbly halo orbit. The plan assumed the rocket would get it in the general direction, and Webb would have to use a good chunk of its own fuel to fine-tune the path. But the Ariane 5 didn't just get it in the general direction. It hit a bullseye from 1 million miles away. The trajectory was so precise, so dead on, that the telescope barely had to fire its thrusters at all to correct its course. And this is the punchline: that fuel it didn't have to use. It's still in the tank. The telescope's lifespan isn't limited by its electronics or its mirrors. It's limited by how much fuel it has to stay in orbit at L2. The original mission was planned for 5, maybe 10 years. But because of that one single perfect launch, the engineers suddenly realized they had enough fuel for 20 years, maybe more. On Christmas Day, the Ariane 5 rocket didn't just deliver a telescope. It delivered a gift. It doubled the mission's life before it had even properly begun. It was the first of hundreds of terrifying single point of failure moments that had to go right, and it went so right it changed the future. But it was just the beginning. The telescope was now hurtling through space, alone, and it still had to unfold. The launch was perfect, a Christmas miracle. But that was just the first domino in a line of 344 single points of failure. The telescope was now on a 29-day journey to its new home at L2, but this wasn't a quiet cruise. This was what the team called the 30 Days of Terror, a month-long, fully automated high-wire act where the most complex piece of origami ever built had to unfold itself, 1 million miles from anyone who could fix it. The whole process started just a few days after launch. First, the two big pallets that held the folded-up sunshield, one at the front and one at the back, swung into place. Then, the whole telescope assembly itself pushed upwards on a deployable tower, rising about 2 meters to get some breathing room. This was a crucial step. It physically separated the cold, sensitive telescope from the hot, noisy bus that held all the computers and communications gear. Then came the moment of truth. The covers that protected the delicate paper-thin sunshield membranes were rolled back. For the first time, the 5 layers of Captain, all folded up like a high-tech accordion, were exposed to space, and now they had to be pulled taut. This is where those 400 pulleys and nearly a quarter-mile of hair-thin cables came into play. Over the course of 2 agonizing days, tiny motors began to whir, slowly, methodically, pulling the 5 layers into their final diamond-shaped configuration. It was the most nail-biting part of the entire deployment. Imagine trying to perfectly stretch 5 bedsheets, each the size of a tennis court, one on top of the other, without letting them touch or snag. Now do it in 0 gravity, using only a bunch of fishing line after they've been crumpled in a box for weeks. The team on Earth could do nothing but watch the telemetry data. A single snagged cable, a single tear in one of the membranes, a single motor failing to turn, and the mission was over. The $10 billion telescope would be cooked by the sun. But the snags never came. The motors didn't fail. Layer by layer, the giant silvery kite was pulled into shape. When the final sensor confirmed that the fifth layer was fully tensioned, a wave of relief washed over mission control. The bonfire was blocked. The telescope was finally in the shade, and the temperature on the cold side began to plummet exactly as planned. The most dangerous part of the deployment was over, but the most delicate part of the origami was still to come. The sunshield was open, but the telescope's golden eye was still folded shut. The telescope was finally in the dark, and it was getting cold. Fast, but it was still blind. The giant golden eye we'd spent decades building was still folded up, tucked away like a sleeping insect. The most dangerous part of the deployment was over, but the most delicate part was about to begin. Next up was a piece of high-stakes mechanical archery, the secondary mirror. This is the little mirror that sits out on the end of 3 long booms, and its job is to catch all the light gathered by the giant 6.5-meter primary mirror and focus it perfectly into the instruments. For launch, it was folded up and tucked away. Now it had to swing out and lock into place. This is one of those things that sounds simple, but the precision required is just silly. The booms unfolded, pushing the mirror out into the void. It had to lock into a final position with an accuracy of about 1.5 millimeters after travelling over 7 meters. It's like trying to hit a target the size of a quarter from the other end of a football field. If it was off by even a tiny fraction, the entire telescope would be permanently out of focus. But the motors whirred, the latches engaged, and the secondary mirror snapped into its final position. Perfect. And then, the grand finale of the origami show. The 2 side wings of the primary mirror, each holding 3 of the precious golden hexagons, had to swing forward. This was the last major moving part. For nearly 2 weeks, the world had been watching this thing unfold piece by piece. This was the final step. Slowly, deliberately, the motors on the portside wing began to turn. The wing swung forward, and after a few hours a series of latches clicked into place, locking it permanently. Then the starboard wing did the same. A final, satisfying click echoed in the silence of mission control. And just like that, it was done. The 30 days of terror were over. The mechanical ballet was complete. For the first time, the James Webb Space Telescope was a telescope, a complete 6.5-meter solid gold eye staring out into the void. The hardware was built, the origami was unfolded, but it still couldn't see a thing. The eye was open, but it was seeing 18 separate blurry images. The work of turning this collection of mirrors into a single, perfect time machine was just about to begin. So the origami was done, the hardware was perfect, but the telescope was still basically useless. The eye was open, but it was seeing 18 different things at once. The next phase of the mission was to turn this collection of 18 separate mirrors into one single, perfect, unified eye. But before they could even start, they had to wait. This was the chill down period. The entire telescope, now in its permanent shadow, had to cool down to its final stable operating temperature of minus 223 degrees Celsius. This took weeks, and it was absolutely critical. Trying to align the mirrors while they were still shrinking and settling from the cold would be like trying to tune a guitar while someone is still tightening the strings. You just have to wait for everything to stop moving. Once it was cold enough, the real work began. The team pointed the $10 billion telescope at a single, bright, boring star, and what they got back was a mess. Not one star, but 18 separate, blurry blobs of light scattered across the detector. This was expected, but it was still a pretty daunting sight. The 18 golden hexagons were acting like 18 separate, cheap telescopes, all looking in slightly different directions. The job now was to get all 18 of those mirrors to act as one, and the way you do that is by nudging them. Very, very carefully. Each mirror segment sits on 7 tiny motors that can move it in microscopic steps. And when we say microscopic, we mean movements on the scale of nanometers. A single sheet of paper is about 100,000 nanometers thick. They were moving these mirrors in steps that were a fraction of a single wavelength of light. Over the next few months, the team on Earth played the world's most expensive high-stakes video game. They nudged one mirror, took a picture, nudged another, took a picture. Slowly, Painstakingly, they herded those 18 blurry blobs of light, bringing them closer and closer together until they stacked perfectly on top of each other. They merged into one, and what they saw wasn't just a dot. It was a single, razor-sharp point of light, blazing with 6 perfect diffraction spikes. That iconic hexagonal starburst shape isn't an accident. It's the signature of the telescope itself, the light bending around the edges of those 18 golden mirrors. It was the proof. The eye was open. The focus was perfect. After decades of work and a month of pure terror, the time machine was finally online. So after all the terror, all the origami, all the nanometer level nudging, it was time. The time machine was online, and the team pointed it at a tiny, seemingly empty patch of the southern sky. The target was a galaxy cluster called SMACS 00723. This thing is so massive its gravity actually bends and magnifies the light from objects behind it, giving us a little cheat code for looking even deeper into the universe. And then, on July 11th, 2022, the world saw what all that work was for: the first deep field image from the James Webb Space Telescope. To understand why this picture broke everyone's brain, you have to remember how Hubble did this. To get its famous ultra-deep field image, Hubble had to stare at a single patch of sky for weeks. The total exposure time was over 11 days, painstakingly collecting one ancient photon at a time from the darkness. The James Webb Space Telescope took this first image in 12.5 hours. And what it sent back was just insane. It wasn't just a sharper version of what Hubble saw, it was a completely new universe. Thousands of galaxies we had never seen before just popped into existence. Tiny, fuzzy red smudges in the old Hubble images resolved into beautiful, complex spiral galaxies with visible structure. And behind them, even more distant, even older galaxies appeared out of the blackness. And here's the really crazy part. The patch of sky they were looking at, it's the size of a grain of sand held at arm's length against the night sky. And in that tiny, tiny speck, we found thousands and thousands of galaxies, each one containing billions of stars and probably trillions of planets. This wasn't just a proof of concept anymore, this was a revelation. The first postcard from the dawn of time had arrived, and it showed us that the universe was bigger, more crowded, and far more spectacular than we had ever dared to imagine. So let's go back to that first image, the one that broke everyone's brain. If you look closely, past all the bright nearby galaxies in the cluster, you'll see some really funky stuff. These weird, stretched-out arcs of light, like someone smeared the picture with their thumb. They look like mistakes, but they're not. They're the most important part of the whole image. This is a phenomenon called gravitational lensing, and it's one of the weirdest and coolest tricks in the entire universe. The basic idea comes from Einstein. He figured out that massive objects, like that huge SMACS 00723 galaxy cluster, don't just sit in space, they warp it. They bend the very fabric of space-time around them. Imagine a bowling ball on a giant rubber sheet. It creates a big dip, right? The physics behind it is all part of general relativity, and honestly the math will make your brain hurt. So let's not worry about that. The point is, space itself can be bent. Now think about the light from a super distant galaxy, something way, way behind that massive cluster. That light has to travel across the universe for billions of years to get to us. And when it passes by the cluster, it has to travel through that warped, bent space. It follows the curve. It's like rolling a marble past the bowling ball on the rubber sheet. It doesn't go in a straight line anymore. It gets bent. And this bending does two incredible things. First, it distorts the image of the background galaxy, stretching it out into those weird arcs and smears. It's a cosmic funhouse mirror. But here's the real magic, the cheat code we talked about. It also magnifies the light. That warped space acts like a giant natural magnifying glass, a telescope built by gravity itself. This means we can see things that would otherwise be completely invisible, even to a machine as powerful as Webb. We're using the gravity of a whole galaxy cluster as a second lens, letting us peer even deeper into the darkness, at galaxies that are even older and fainter. Those weird smeared lines of light. Some of them are the oldest things humanity has ever seen. They're ghosts from the dawn of time, and we're only able to see them because the universe decided to give us a free telescope. So that gravitational lensing trick is our cheat code. It's how we use the universe's own gravity to get a free zoom lens and peek at the most distant, faintest things imaginable. But what happens when we turn the cheat code off? What happens when we just point the telescope at a patch of sky that looks completely, totally empty and just stare? This is where the first real shock of the James Webb era came from. The story we'd been telling ourselves for decades, the one based on all our best models and theories, was pretty simple. After the Big Bang, there was a long period of darkness. Then, slowly, gradually, the first tiny, clumpy, disorganized baby galaxies would start to form. It was supposed to be a slow, quiet dawn. We expected to find a few faint smudges, the first flickers of light in the cosmic nursery. But that's not what Webb saw. Not even close. It was like walking into what you thought was an empty room and finding a full-blown dance party already in progress. The telescope found big, bright, well-structured galaxies that were already shockingly mature. And they were showing up way, way earlier than anyone thought possible. The poster child for this new mystery is a little red smudge called Jade's GS Z13-0. It's not a catchy name, but it's one of the most important objects ever discovered. We're seeing it as it was just 320 million years after the Big Bang. To put that in perspective, if the entire 13.8 billion year history of the universe was a single year, this galaxy was already up and running on January 8th. And it wasn't just a little clump of stars, it was a proper galaxy, shining with the light of a billion suns. This just shouldn't be possible. The models didn't allow for it. There simply wasn't enough time for a galaxy to gather that much gas, form that many stars, and get that big, that fast. It's like looking at a photograph of the Earth from 4.5 billion years ago and finding a fully built Roman Colosseum. It just shouldn't be there. This one little red dot and others like it didn't just add a new chapter to the textbook, it ripped the whole book apart. The smooth, gradual story of cosmic evolution was wrong. The universe, it turns out, skipped its awkward teenage years and went straight to being a grown-up. And now, scientists are scrambling to figure out how. This is why we built the telescope. Not to confirm what we knew, but to find out just how wrong we were. This is where the story goes from surprising to completely impossible. That little red dot and the others like it aren't just fun new discoveries. They're a direct frontal assault on our entire understanding of how the universe is put together. Let's break down exactly why these things are such a headache. The story we've been telling ourselves for decades is called the bottom-up model of cosmology. It's a slow, patient story. The idea is that after the Big Bang, tiny fluctuations in the density of dark matter started to pull together into small clumps, or halos. These little halos of gravity then slowly, gradually, began to pull in the hydrogen and helium gas that filled the early universe. Over hundreds of millions of years, that gas would cool, form the first stars, and create the first tiny, messy, disorganized baby galaxies. Then, those baby galaxies would smash into each other and merge, getting bigger and bigger over billions of years. It's a slow, patient process of cosmic construction. Or at least it was supposed to be. What Webb is seeing throws that whole timeline in the trash. The galaxies it's finding are just too massive, too fast. According to the bottom-up model, there simply wasn't enough time for a galaxy to gather that much gas and form that many stars. It's like planning to build a garden shed and coming back a week later to find a fully built skyscraper. You just stand there and ask, where did all the materials come from, and how did you build it that fast? That's the question astronomers are asking now. And as if that wasn't strange enough, it's not just that they're big, they're also weirdly well behaved. The early universe was supposed to be a chaotic place, a cosmic mosh pit of small galaxies smashing into each other. We expected to see messy, clumpy, irregular blobs. But some of these early galaxies are showing signs of structure. They have bright, concentrated centers and even hints of flattened disks. That kind of organization takes time. It takes gravity a long while to settle everything down into a neat spinning disk. Finding one this early is like finding a perfectly smooth round stone in the middle of a rock slide. It just doesn't fit the picture of chaos. So it's not one problem. It's a whole collection of them. They're too big, they're too bright, and they're too organized. They're impossible galaxies, and they're not a rare fluke. Webb is finding them all over the place. This means our fundamental story of how the universe grew up is, at best, incomplete. And at worst, it's just plain wrong. So what do you do when you find a whole bunch of stuff that shouldn't exist? You've got two choices. Either your clock is wrong, or the rulebook you've been using is complete garbage. And right now, astronomers are seriously considering both. Let's start with the clock. Maybe the universe is just older than we think. Maybe that skyscraper didn't get built in a week because the calendar was wrong, and it was actually a month. The problem is, the age of the universe, 13.8 billion years, is one of the most solid, well-tested numbers in all of science. It's backed up by mountains of evidence, from the expansion rate of the universe to the faint leftover heat from the Big Bang itself. To change that number, you'd have to break a whole lot of other physics. It's not impossible, but it's a really, really long shot. That leaves us with the other option, which is way weirder and way more exciting. Maybe the rulebook is wrong. Maybe our whole bottom-up story of how galaxies are built is just not how it happened back then. What if the early universe had a cheat code? One idea is that galaxy formation wasn't just a slow, bottom-up process. What if it could also be top-down? Instead of slowly building little galaxies and smashing them together, what if massive galaxy-sized clouds of gas could collapse directly under their own gravity and form a huge galaxy all at once? Not building a skyscraper brick by brick, but 3D printing the whole thing in one go. That would explain the size and the speed. Or maybe the problem isn't the galaxies, but the stars inside them. The first stars were supposed to be big, but what if some of them were true monsters? Unimaginably huge stars, hundreds of thousands of times the mass of our sun, that burned with a fury we can barely comprehend. These things would have lived fast and died young, exploding in blasts that would make a normal supernova look like a firecracker. They would have seeded the early universe with heavy elements at a furious rate, basically kick-starting the whole process of galaxy evolution into hyperdrive. So we're left with a choice: a broken timeline or a completely different kind of physics in the cosmic dark ages. Did the universe have more time, or did it just have better tools? That's the mystery. And finding the answer is what this $10 billion time machine was really built for. So for the last few minutes, we've been talking about how the James Webb Space Telescope is a time machine, a $10 billion machine for staring into the abyss and finding impossible galaxies that break all our rules, and that's its main job. It's what it was built for. But that's only half the story, and this is where things get really, really cool. Because it turns out this telescope has a secret secondary mission. It's not just a time machine for looking at the edge of the universe, it's also a neighbourhood watch, a tool for spying on the planets right next door. Let's talk about a trick called transit spectroscopy. It's a fancy name for a pretty simple idea. We find planets around other stars by watching them pass in front of that star. It's called a transit. From our perspective, the star's light gets just a tiny, tiny bit dimmer. It's like watching a moth fly in front of a distant streetlight. That little dip in brightness tells us something is there and how big it is. But here's the genius part. As that planet passes in front of its star, a tiny sliver of the starlight shines directly through the planet's atmosphere, if it has one, and that atmosphere acts like a filter. It's like looking at a white light through a piece of stained glass. Certain colours get blocked. Different gases in an atmosphere absorb very specific wavelengths of light. Water vapour absorbs certain colours, methane absorbs other colours, carbon dioxide absorbs others still. Each gas leaves a unique telltale fingerprint on the light that passes through it, a chemical barcode. So by looking at the starlight that has been filtered through a planet's air, we can read that barcode. We can figure out what that atmosphere is made of. We can, for all intents and purposes, sniff the air on a planet hundreds of light years away. And this is why Webb is so perfect for the job. Many of those key ingredients we're looking for, water, methane, the building blocks of life, their barcodes are written in infrared light. The exact same kind of light Webb was built to see. So the same hardware that lets us see the first galaxies also lets us hunt for the ingredients of life in our own cosmic backyard. The time machine is also a planet sniffer, and its second job is just getting started. So, okay, the planet sniffer, that's the theory. But does it actually work? Time for a road test. The team needed a good first target and they found a perfect one, a planet called WASP 39b. This thing is what we call a hot Saturn. It's a big, puffy gas giant orbiting insanely close to its star, completing a full year in just 4 Earth days. It's not a place you'd want to visit, but its atmosphere is huge and bloated, making it a perfect, easy target for a first try. It's like trying to hit the side of a barn with a baseball. A very big, very hot, very distant barn. Webb stared as the planet passed in front of its star, and it watched the starlight filter through that puffy atmosphere. And the first thing it spotted was a slam dunk. A huge, crystal-clear chemical barcode for carbon dioxide. No ambiguity, no guessing. It was just there. This was the first time we had ever definitively detected CO2 in the atmosphere of a planet outside our solar system. The planet sniffer worked. It was a huge success. But then they saw something else. A funky signal in the data that nobody was expecting. A chemical fingerprint for sulfur dioxide. And this is where the story goes from cool to completely mind-blowing. See, sulfur dioxide is a weird one. It's an unstable molecule. It doesn't just like to hang around. The only way you get a bunch of it in an atmosphere is if something is actively making it, right now. And that something is the star's own light. It's called photochemistry, a fancy word for light-powered chemistry. The star's intense ultraviolet light is literally smashing other sulfur-bearing molecules apart, and the pieces are recombining to form this new stuff. It's like the star's light is a cosmic demolition crew, breaking down buildings, and the rubble is being used to build something new. The sulfur dioxide is that new building. And this is the punchline. We didn't just sniff the air on another planet, we saw the weather. We saw an active dynamic chemical factory running on a planet hundreds of light years away, powered by its star. This proves we can do more than just take an inventory of what's there. We can analyze the processes that are happening. The neighborhood watch just got a whole lot more powerful, and that's a huge step, because life, as we know it, is also a chemical factory. Okay, so we've talked about Webb as a time machine, and we've talked about it as a planet sniffer. But one of its most mind-blowing abilities is just its power to see through things that are in the way. It's a ghost viewer, and there's no better example of this than what it did to one of the most famous astronomical images of all time. You know the picture, the Pillars of Creation. Hubble took it in 1995, and it became an instant icon. These three colossal towers of interstellar gas and dust, silhouetted against a backdrop of stars. It looks like a ghostly hand reaching out into the cosmos. It's beautiful, it's epic, and it's basically a lie, or at least it's only half the story. Because what you're seeing in that Hubble picture isn't just a cloud, it's a wall of cosmic smoke. The pillars are a stellar nursery, a place where new stars are being born. But all that dust is so thick that visible light can't get through it. Hubble was basically just taking a picture of the outside of the nursery. It could see the building, but it couldn't see any of the babies inside. And then Webb looked at it. And the wall just dissolved. In Webb's infrared view, those thick, opaque pillars of dust become translucent and ghostly. You can see right through them, and what's inside is just insane. Thousands and thousands of brand new stars blazing away where before there was only darkness. They show up as these tiny, brilliant red dots, still wrapped in their dusty cocoons. These are stars that are only a few 100,000 years old. They're cosmic infants. This is the power of infrared. It's like the universe's own ultrasound. Visible light gets blocked by the dust, but the longer wavelengths of infrared light sail right on through. For the first time, we're not just looking at the outside of the stellar nursery. We're seeing right into the delivery room. We're watching the process of starbirth as it happens, catching these baby stars in their very first moments of life. That iconic picture we all knew and loved. It was just the curtain. Webb just pulled it back. So Webb pulled back the curtain on the Pillars of Creation, and the wall of smoke just dissolved. But this isn't just about getting one new spectacular desktop background. It's about seeing the whole process. That ghost viewing power lets us watch the raw ingredients of the cosmos, the dust and gas, get pulled together to build new stars and new solar systems from scratch. We're not just seeing the nursery, we're in the delivery room. And when you put that next to its other secret mission, the planet sniffing, you realize what's really going on here. On one hand, Webb is watching the construction sites, seeing the raw materials for future planets. On the other, it's analyzing the finished product, tasting the air on worlds that formed billions of years ago. It's the entire story of creation, from dusty cloud to dynamic atmosphere, all seen by the same golden eye. So that's the machine we built. It's not one thing, It's at least 3. It's a time machine, staring back to the cosmic dawn and finding impossible galaxies that are bigger and brighter than our rulebook allows. It's a neighborhood watch, sniffing out the chemical weather on planets hundreds of light years away. And it's a ghost viewer, piercing through cosmic walls to watch baby stars switch on for the very first time. It's the most powerful, most complex, and most expensive scientific instrument humanity has ever flung into the void. And here's the real punchline. After all of it, the decades of work, the toxic metal, the origami, the $10 billion, the 30 days of pure terror, the mission has barely even started. Thanks to that one single, impossibly perfect launch, we didn't just get the telescope we planned for, we got double. 20 years of fuel, maybe more. 20 years of staring into the dark. The first images didn't give us the answers we were looking for. They just broke our textbooks. They told us our story of how the universe grew up was wrong. They showed us that the cosmos is weirder, faster, and more spectacular than we ever dared to imagine. This $10 billion machine wasn't built to confirm what we know. It was built to show us just how much we don't. It's a question-generating engine, and it's just warming up. The story of what we thought was out there is over. The story of what's really out there is just beginning.